Hello? Oh, hold on. Cool. Okay, I think that's sorted out. Wait for a couple more minutes. Has everyone submitted their homework? Had any trouble on Gradescope? No? You can unmute. Okay, so it's 11 a.m. We can get started. The first thing I wanted to just remind you is about both the Gradescope and CBTF scheduler. So we'll be conducting exams through the CBTF scheduler. Your first exam is still a ways away, but I think they would like you to basically sign up for this course on CBTF scheduler, and then you'll get reminders and so on about your exams. So go ahead and add 490 on your CBTF schedule. And there's a link on the website that will take you there. Okay, so please do that as soon as you can. So the link is right there. It's on the main page. And of course, with Gradescope, I'm sure when you submitted your first homework assignment, which was due before class, so you should have created an account for yourself on Gradescope to be able to do that. So hopefully you're all set on that. So the exam will basically be posted on Gradescope, and you'll take it on CBTF and upload your scan solutions on Gradescope. So that'll be the procedure. Any questions about that? You guys can hear me, right? So somebody confirm that you can hear me.
Yes, we can hear you.
Okay.
Yes, we can hear you.
All right. So, let's briefly go over the previous lecture, just to remind ourselves what we're doing, because it's been a few days. And you guys had a supposedly long weekend, but I guess it doesn't really make a difference in COVID times. So we were talking about convex functions and convex sets, and basically some characterizations of convex functions using the first and second derivatives, or using the gradient and the Hessian. Okay, so basically, a nice thing about convex functions is that if you have a local minimum, it's also a global minimum. If it's strictly convex, that minimum is unique, right? And then we said, well, a convex function is basically underestimated by the first order Taylor expansion. So the necessary and sufficient condition for convexity is that Fy is greater than the first order Taylor expansion for Fy in terms of Fx, right? And so we showed that, and then we looked at second order characterizations of a convex function, and we said that if the Hessian is PSD, then that implies that F is convex. Now F is convex on S, but and S being open, if S is open, then you can easily prove the implication going the other way, and that's what we showed later. So the PSD condition is if and only if, with the caveat that to go backwards you need the open S condition, or at least to prove it easily. Of course, the strict a positive definite condition basically goes only one way. So if a function is positive definite, that means that F is strictly convex on S, but F can be strictly convex without F being positive definite. I mean, and the example we showed was the x to the fourth, which you proved in homework 1 was strictly convex, but the second derivative, in this case, the special case of Hessian, is 0 at x equals 0. Okay. All right. So and then we looked at some special cases, an affine function, which is somebody needs to mute, I guess. Let's see. It looks like it's Samirat. You may want to mute because I can. Yeah, I'm going to mute you. Okay. All right. So then, if F is an affine function, A transpose X plus B, that's both convex and concave, but not strict. A quadratic function, the necessary and sufficient conditions for F being convex, strictly convex, concave, and strictly concave are completely based on the matrix Q that defines the quadratic. Okay, so that's the result that we showed. So in this special case, actually, strict convexity implies F is strictly convex and quadratic implies that Q must be positive definite. So in this special case, you can go both ways. Okay, and we proved that. Okay, and then we looked at some examples on how to find. Oh, by the way, there was a question on Piazza. So a matrix is positive. To check for a matrix being positive definite or positive semi-definite is based on the leading principal minus. Leading principal minus or principal minus, depending on whether you want to check PSD or PD. But to check that a matrix is NSD or ND, you need to basically show that negative A is PSD or PD. Okay, so that's the test. So if you want to use a leading principal minor test, you need to test and you want to see whether it's negative definite or not. So that's what we did here, you see. Basically, we looked at minus Q and showed that the principal minor is a principal minor that's negative, and so Q is non-NSD. Okay, so I think that's all I want to say about the last lecture. Oh yeah, and clearly, for a convex function, if you basically find a point at which the gradient is 0, you've found a global minimum for the problem. You've solved the problem. Okay, and we did an example of that. But in general, actually finding a point at which the gradient is 0 may be just as difficult as the original optimization problem. Okay, and we saw a simple example of that last time. And so what we're going to develop from today's lecture on are gradient methods for actually approaching the point at which the gradient is 0. Okay, or to basically gradient methods for getting to what are called stationary points. And if it's a convex function, of course, that stationary point will also correspond to a global minimum. So that gets us to today's lecture. Okay. Okay. So, what are gradient methods? Okay, so let's first look at the case of unconstrained minimization of a continuously differentiable function. Okay, and we may assume that it's also twice continuously differentiable when we do analysis of what the rate of convergence. We'll get to a little bit later. Okay, but for now, just assume that it's continuously differentiable. And so, what's the iterative way to try and get to the minimal of the function? So the idea is basically you in iterative methods, you create a sequence, you generate a sequence of x's, of points. So start at some x0 and then generate x1, x2, and so on, such that the function at the next iteration, f of xk plus 1, is less than f xk. That's the goal. Okay. And then the hope is that if you can do this, you can decrease f all the way to the minimum. Of course, that's not necessarily going to happen. And we'll see why and why not as we go along. Okay. Okay. So let's first look at what's called the steepest descent procedure, the one that basically will somehow try and decrease f, go in a direction, at least that would try and decrease f as much as possible. So in steepest descent, you move xk in a direction that in the direction, I'm not saying that it's the value, but it's just the direction that decreases the function the most. So what is that direction? Okay, again, somebody is not muted, it looks like. I believe that's Rizal, unless you got, if you only unmute yourself if you have a question, okay? Otherwise it creates some noise. Okay. All right, okay. So, so move xk in the direction that decreases the function most. And I claim that this direction is the negative of the gradient. And let's see why. Okay, so to see why, let's say you look at some direction v, direction vector v, okay? V belonging to Rn and v is some non-zero vector. And suppose I move f, move x rather, by some amount epsilon in the direction of v. So I go from x to epsilon times, to x plus epsilon times v. Okay, so we know by a Taylor series expansion that this is f of x, the first order Taylor series expansion. This is going to be this plus transpose v. We saw this earlier, 2 lectures ago, plus little o of epsilon. Okay, so if you look at the rate of change of f along direction v, I mean, this is basically the definition of the gradient, essentially. So this says that this is, if I look at the rate of change of x, the amount by which x changes divided by epsilon, this becomes basically just plugging in from this equation up here, subtracting f on this side, dividing by epsilon, you're left with this. So this is exactly the gradient of f transpose v. No surprise there. Okay, but if you look at this quantity, so this is the rate of change along direction v. It is gradient of f times the transpose v. But the Cauchy-Schwarz inequality, we know that this is less than or equal to what? Anyone? Koshish was? Yeah? Anyone going to speak? You can unmute. I'm sorry if I muted you, but you can unmute if you want to answer. Okay. Nobody's going to answer, so I'm going to write it down. Right? So it's upper bounded by that. And in fact, the absolute value of the inner product is upper bounded by that. So the inner product itself is lower bounded by the negative of the product of the norms. And you have equality on the left-hand side if and only if what condition holds on V. I'm sorry, this should have been gradient. So V has to be what for equality on the left-hand side? Yeah? Anyone?
The negative of the gradient vector.
Very good. So it'll be negative of the gradient vector. Right? And in fact, you can scale it by some positive beta, but it's along the direction. So the maximum rate of decrease of F at any point X is in the direction of the negative gradient. Okay, so when you go in that direction at any point at time k or at xk, and you move in the direction of the negative, the gradient, you decrease the function most, and that's called the steepest descent approach. So we'll see why this may not necessarily be the best approach, but that's one way to go down to try and make F smaller, right? All right. So let's, of course, we have to assume that the gradient is non-zero. Otherwise, you're going to be multiplying by something that's zero, and you're not going to change anything. So assuming that the gradient at xk is not zero, to go from xk to xk plus 1, we move along negative of the gradient, which means that xk plus 1 should be xk minus some alpha k times gradient of xk, where this alpha k, which is positive, is called the step size. At time k. So basically, alpha k controls the movement along the gradient, or negative gradient, I should say. So if alpha k is too large, the function may actually increase. Why is that? So let's see. So if I make my step size very large, then even though I'm going along the negative gradient, I may actually end up increasing the function value. And let's see why in this simple example here. We have a quadratic, right? We have a quadratic function. Okay, and let's say this is xk at time k. And we see here that at this value of xk, the gradient is positive. Okay, and this is my x-axis, is one-dimensional. So if the gradient is positive at this point, what the gradient descent procedure, steepest descent, says is that I should move xk in this direction, okay, by the amount alpha times the value of the gradient, right? So suppose I moved by it's alpha k is such that I move my xk to this point here and make that xk plus 1. Then, of course, I've decreased f. So f has gone from here to here. But what if instead I went, I made alpha k even larger, then I go from here, say, all the way up to this point here, and this is my xk plus 1. Then the value here is actually larger than the value here. Right? So you have to be careful about choosing your step size. So even though you're going along the direction of maximum decrease of the function, you may end up actually increasing the function value if you take a large step size. So you need to choose this alpha k carefully. We'll see how we do that. Any questions? Okay, and there's actually a 2D example in your textbook, and I've reproduced that here. I can't put this in your lecture notes because copyright issues, but I can just display it in class. So here, so if you want to see this figure, just go to your textbook. So basically, the idea here is this is a little more complicated to draw, which is why I just took it from the book. So you're here at point X in the two-dimensional plane, okay, and the value at this value, this fx takes the value c1, and these are the level curves where fx takes all the values of x for which fx takes the value c1. Okay, so that's that level curve. And the gradient, of course, is in this direction. It's going in this direction. So in order to decrease the function or to do steepest descent, you'll try and go in this direction, opposite of the gradient. So if you did that, okay, then you go up here, you do get a smaller value, C2 less than C1. This is a level curve for C2, which is smaller than C1. And then you go further, you get to C3. But at this point, if you go even further, then you start to increase again, get back to C2, and you make it this large. Eventually, you're going to exceed the value of the function C1 that you originally started with. Okay, so this is a way to visualize steepest descent and the step size in 2 dimensions. Any questions? Okay. Now let's talk about a general gradient descent algorithm. And a general gradient descent algorithm, these are also called gradient-based algorithms, or simply gradient algorithms, but not steepest descent. Steepest descent is referred to is reserved for the one that actually uses a negative gradient. Okay, and what are these algorithms? In these algorithms, we'll let xk plus 1 equal xk plus alpha k times some dk. And dk is a vector, n-dimensional vector, such that if I look at the inner product of f at xk, the gradient at xk times dk, this is negative. Okay, so I'm again actually trying to go in a direction that will try and decrease the function, but it's not exactly along the gradient. It's not along the steepest direction necessarily. And there may be some advantages in doing that in practice, because if you're going along the steepest direction, as we saw, you may actually overshoot and increase the value of f. Okay, so, and you can actually improve convergence rates and so on by choosing a dk that's different from the negative gradient. But basically what this is saying is that if I look at the negative gradient and project it along dk, I get something positive. So dk has a positive projection along the negative of the gradient. If I do that, then for alpha k small enough, I'm still going to decrease the function if I start with a gradient that's non-zero at time k, right? So basically, of course, if dk is just the negative gradient itself, you get the steepest descent algorithm. And often you construct this dk through a matrix, capital dk. So this little dk is actually a matrix capital dk times the gradient time k. And why is this? Why does this work? But if you look at dk transpose gradient of fk, this is minus gradient of fxk transpose dk gradient of fxk, right? Just multiplying. And this is, since dk is a positive definite, this is a PD matrix. So if I pre-multiply and post-multiply by any vector that's non-zero, I'm going to get something negative. So this will be negative if the gradient at point k is not equal to 0. Okay. So that's the more general gradient descent algorithm, where you're not going along the negative gradient, but you're going along a direction that has a positive projection along the negative gradient. Let's look at a figure for that from your textbook. So here's the same level curves that we had for steepest descent, C1, C2, C3, sorry, C1, C2, C3. And now here I'm at X, the gradient direction is this. So and the negative gradient direction is this way. This is negative. And if I go in a direction that has a positive projection along this direction, which something like this maybe, which is not quite along the negative gradient, but this what are these called? Acute angle, I guess, acute angle with respect to this. Then you see that you'll still decrease the function, but of course, if you make the step size too large, you still have the problem that you might go beyond what you started out with. Okay. All right. Any questions? Questions? Somebody tried to unmute, so if you have a question, please unmute and ask or chat. Okay. All right. If there are no questions, let's move along. So let's talk about step size. Okay. So a common choice for the step size is to make it alpha k equal to alpha for all k. So constant step size or fixed step size. But this can have some issues with convergence. And we'll talk about that a little bit later. Okay, you have to be careful about the choice of alpha k, right? And alpha k that is small enough. Okay, maybe you can find an alpha k small enough that your algorithm will converge. But then if you choose it a little large, then you may actually end up diverging. And we'll actually see examples of that in just a second. Okay. Another option is to choose alpha k at every time k, so as to guarantee that f always goes down. Okay, and one way to guarantee that, a very straightforward way, at least to think about it, is to just say I'm going to choose my step size, the smallest step size, such that f of xk, sorry, not smallest step size, a step size that's in fact the largest step size for which I still or a step size for which I get the largest amount of decrease in the function. So I want to minimize the function at the next time step. Okay. So choose the alpha that will give you the smallest value for this. This will be basically correspond to xk plus 1, right? So choose the alpha at time k to make f at xk plus 1 the smallest possible. Okay, but this may be difficult to do in practice because you're solving another optimization problem essentially. In some cases, if f has a nice form, you can actually solve this explicitly, right? Even if you can't solve the original optimization problem, you might be able to solve this one. But in general, it's going to be difficult. So there's actually an interesting practical alternative to this, and these are called backtracking or successive step size reduction algorithms. And the most commonly used one is what's called Armijo's rule. Okay, Armijo was a mathematician, I think, who worked in somewhere in Texas at Rice Institute in Texas, and he has a couple of papers to his name. So if you go on Google and search for papers by Armijo in this, at least in this context, you'll find a couple of papers, and they're both cited very well. So he didn't do that much work in the area, but whatever he did was cited very well, and that's a good thing to have. So this is called Armijo's rule. So in Armijo's rule, what you do is you successively decrease alpha, so that you make sure that the function value at the next iteration is smaller than the function value at the current iteration. Okay, so how do you do this? So you exploit the fact that if you look at the first order expansion of xk plus alpha, f of xk plus alpha dk, this is f of xk plus alpha times the gradient plus little o of alpha, right? And so this is negative by construction of dk. So if alpha is sufficiently small, we know that f decreases from time step k to time step k plus 1. But we don't want alpha to be too small. What's wrong with an alpha that's too small? Anyone? I mean,
it will take sorry.
Yeah, go ahead.
It will take.
It'll take what? Go ahead and unmute. Yeah. Don't be shy.
It will take too long to converge.
Yeah, very good. So it might take a long time to converge. So it's slow convergence. So what you do is basically start with some maybe large value of alpha, and then try and decrease it, right? So, but of course you have to, there's still some experimentation to figure out what the starting value of alpha should be. But there are some guidelines that are given in the book. So we'll start with some alpha equal to alpha 0, and under the assumption that alpha 0 is going to be too large, right? And then you take you have these parameters to basically which allow you to decrease alpha. And the way you do it is as follows: you have a parameter sigma and a parameter beta, with both less than 1, both between 0 and 1, positive and less than 1. And you look at the value of f of xk plus alpha dk, which you can compute easily, right? Because you have the function form. So you look at that and then compare it to f of xk plus sigma times alpha gradient of xk transpose dk. Okay. Now, if this is less, I mean, of course, this quantity is negative, right? This quantity is negative. Okay, and sigma and alpha are both positive. So you have basically decreased f by some amount, right? And the amount by which you decrease is determined by these parameters sigma and alpha. And so this happens, you have decreased your f. It may not be the maximum decrease in f, but you've at least ensured your decreased f, and then you stop. You stop at this point. Okay, but if the reverse is true and the inequality went the other way, so if the inequality went this way, then I decrease my alpha. I say that my alpha was too aggressive, too large, So I'm going to decrease my step size. And the way I decrease my step size is I do it geometrically by multiplying it by beta, which is less than 1. So I'll set my alpha equal to beta times the previous alpha, and then go back to step 2 and check again. So I might do this a few times before the inequality is met in step 2. Okay. And so I'll basically stop this. I'll terminate this successive decrease in step size after m stages, basically, and I choose the smallest integer m such that the condition in 2 is met, right? And at that smallest integer m, basically, I might have decreased my initial alpha 0 by beta to the m. Okay, and at that point, my condition was met. Okay, so basically, this thing here is my alpha k at that point. Okay, so and the smallest integer, say m is mk, so that would be alpha k, and alpha k satisfies this. This is alpha k. Okay, so that's what Army-Hill's rule does. So it ensures that the function value always decreases in each iteration, and make sure that it's not too large and not too small. That's what it does. Okay, and there are some ways to initialize and choose these parameters, and so you can look at the book for that. Okay, and I suggested some things that I got off the book, but there's more discussion of this in the book. Any questions about Army-Hill?
So right now, like at step 3, it sets alpha to beta alpha. Would it be better if we do something like for example, like an optimal line search here to kind of like, so it's like a lazy line search. You know, we only do line search when it kind of, you know, like overshoot.
Yeah, but the line search itself might be expensive, right, to do, unless you can actually easily do it analytically. If you can do it easily analytically, you would as well have done this, right? So, but there are variants to this. This is not the only way in which you can select the decreasing step size. There's something called Goldstein's rule, and there are other variants too. So, but I guess Army-Ho was one of the first to suggest this, and it's actually a method that works well, and that's why it's used and it's popular.
Okay, that makes sense. Thank you.
All right, so now actually let's study the convergence. So what we're saying is that as long as we choose a step size carefully and we're going in a direction that's of descent, essentially, either the steepest descent or some other direction of descent, right? That has a positive projection with respect to the negative gradient. Then you can make the function decrease. But at some point, the function is not going to be decrease anymore. And intuitively, what's that point? The point at which the function is not going to decrease anymore with these gradient descent procedures. At what point will the procedure stop? Intuitively.
The stationary point?
At a stationary point, at the point at which the gradient is 0, right? Okay, so that's what we're going to try and establish for these gradient descent algorithms. We're going to see, can we show that as k goes to infinity, that we're going to get to a stationary point. And of course, if the function is convex, that stationary point is also a global minimum. Because the function is not convex, the stationary point could be a saddle point. It could also be a maximum if you're really unlucky. Okay, it could be a local maximum, but that's rare, and there's actually a theorem to show that that's not going to happen usually, and we'll talk about that later. But if you're choosing a step size carefully, you're not going to go to a maximum. You're going to go to a minimum. Okay, but you still have to show that. You have to still show that you may end up, not actually getting to a stationary point at all, right? That's also possible. So you have to prove that that's the case. So to understand that, let's first talk about some background about limit points of sequences. Okay, so let's look at a sequence xk in Rn, a point x bar belonging to Rn, and we actually briefly mentioned limit points before, and this is something you should have seen in an undergraduate course, but maybe not in necessarily in Rn. Okay, but basically a limit point, a point x bar is called a limit point if actually the definition is quite obvious. So there's a subsequence of xk, of the sequence xk, that converges to x bar. Okay, and mathematically we'll write it this way: limit of xk as k goes to infinity, but k belongs to some subsequence index set. So this is the indices of the subsequence. I'll give an example in just a minute. So if you only go along the indices of the subsequence and take k to infinity, you will get x bar. Okay, so that's called a limit point. Now, a sequence in Rn, a bounded sequence in Rn actually, converges if and only if it has a unique limit point. There's only one limit point. Then we say it converges. Okay, and if the largest limit point, what's that called? The largest limit point of the sequence is called the supremum, and the smallest limit point is called the infimum. So, and the infimum and supremum may be different from each other, and if they're equal to each other, then there's only one limit point, and that sequence converges. Okay. Now, every bounded sequence has at least one limit point. These are all obvious things, right? Let's do a quick example. Suppose xk is -1 to the power k. This is r to r. So function on the real line. So what are the limit points of this? Anyone?
-1 and 1.
-1 and 1, right? So if you look at all the odd indices, you get -1. All the even indices, you have 1. Okay, so this sequence doesn't converge because it has two limit points, -1 and 1. Okay, but if you look at the sequence half to the k, this converges to 0, right? How about xk equal to -half to the k? This also seems like it's oscillating, but this also has only one limit point, right? So it basically goes from starts at 1, and then -half, and plus 1/4, and so on. It alternates signs just like the -1 to the k. But of course, these values are getting smaller, so there's only one limit point, and this also converges to 0. Okay. So everyone understand the difference between limit points and limits? Okay. So if a sequence converges to some limit, that of course is the limit point of the sequence. But if sequence doesn't converge, it could have multiple limit points. It could even diverge to infinity. Okay, so. But if it's bounded, it's going to have at least one limit point. Okay, so now let's look at, it is time for a short break, isn't it? So let's take a 2-minute break, get back at 11:45, and then we'll talk about how to prove that Armijos' rule converges. Okay, it's an interesting proof. And there are some steps that we'll actually keep using later in the course. So I thought I should go through the details of the proof. Okay. So any quick questions before we take our break?
So just a question for the previous part, for the general gradient descent part. So I think you stated that the xk plus 1 equals to xk plus alpha dk, where dk is projects positively on the negative of the gradient.
Correct.
So is there like any rule for like choosing dk, or is that not the topic of today's lecture?
So generally in most of the proofs that we do, we'll talk about steepest descent, right? But the book actually talks about other choices of dk, and a common choice, and we'll actually come across one a little bit later as well. A common choice, I mean, we talk about what's called Newton's method, but a common choice is when you make, where is it? Yeah, here. So when you choose your dk as some positive definite matrix, a negative of a positive definite matrix times the gradient, right? Then you're ensured that you're going to get a positive projection along the gradient, and then you can choose the structure of this matrix to give you nice properties. Okay, and actually you'll study exactly this example and some convergence for a dk algorithm in one of your homework problems. Okay, and the rate of convergence and so on will depend on the eigenvalues of this matrix. Okay.
Okay.
Right? Sense?
Yeah.
Okay. So we'll talk about that. So let's take our short break now. I'm back in 2 minutes. Okay, let's get started on the proof of convergence for our Amiot's rule. Okay, and this is, we'll look at steepest descent, right, with Amiot's rule. So we saw that already, that with Amiot's rule, basically you had, maybe I should go back and remind you of Amiot's rule. So you have alpha k dk, right? And at the time you stop, f of xk plus alpha k dk is less than this, plus sigma times alpha k plus fk, grad fk transpose dk. But if dk is the same as the negative gradient, so then this will become minus of this product there. So that's what we have here. At the stopping time, we have, so alpha k is alpha 0 times mk, beta to the mk, but mk is the smallest m such that, so this will become alpha k. This is mk, this is alpha k, but there's a negative sign here because I'm going along the steepest descent direction. So instead of grad f transpose d, I have grad f norm squared with a negative sign. Okay, all right, so we'll keep this equation in mind for Amiot's rule at the time we stop. Of course, before we stop, the inequality will go the other way, right? So when we do the step size reduction, before we stop doing this step size reduction, until we get to the to the value of m that satisfies this inequality, it's going to go the other way. Okay, that's also going to be useful to know. Okay, so what this is saying is that as long as the function doesn't go off to minus infinity, that means the minimum is, or the infimum is lower bounded, right? Then every limit point of x is a stationary point for this Amiot's rule, steepest descent. And by stationary point, basically grad f x bar is equal to 0. So in the limit, then if you have take any limit point of my xk may not converge, but it just like, minus 1 to the k, it didn't converge. But what this is saying is that even if it doesn't converge, all its limit points are going to be stationary points. So in the worst case, what will happen is you may, the xk might just shuttle between two stationary points. Okay, but both of those stationary points, both of those points will have gradient equal to 0. Okay, so now let's establish this result. So the way we prove it is again by contradiction, just like a lot of the proofs we've done in class so far, right? So we assume that x bar is a limit point of xk such that the gradient is not 0, and then we get a contradiction. So we'll build a contradiction basically. So assume that this is not 0, we'll build a contradiction. Now, since f, my function is monotonically non-increasing, right? Monotonically, sorry, not the function, but f of xk by construction, Amiot's rule, is monotonically non-increasing and bounded below. Monotonically non-increasing. In fact, it will be decreasing as long as the gradient is non-zero. And bounded below. So if you look at the function sequence, the sequence of function values, this is a monotonically non-increasing sequence that's bounded below. And so any sequence that is bounded below and it's basically monotonically non-increasing, or think of it as decreasing, then it can't go below this lower threshold, so it has to converge. But this is not xk that's converging, but it's f of xk that's converging. The function values are converging. Okay, And f is a continuous function, right? In fact, it's continuously differentiable, so it has to be at least continuous. So if I take any limit point of the sequence xk, and I look at the function value at that limit point, that's also going to be a limit point for the function sequence by definition of continuity. So f of x bar is a limit point of the sequence fxk. Okay, so but the sequence converges. So if it converges, then all the limit points of fxk must be equal to each other. And so the limit of fxk must equal f of x bar, which says that f of xk minus, if I look at the difference between the function value at xk and the function value at xk plus 1, that difference, since the sequence converges, this has to go to 0. Right? This is the Cauchy condition for convergence. And let's call this equation star. Okay, as because k goes to infinity. Okay, so far so good, right? From our condition that the function is bounded below, right? We know that this function of and the fact that Amigo's rule always is guaranteed to decrease the function, at least not increase the function. We now know that the sequence of the function values at the different iterates is going to converge, and it has to converge to f of x bar if x bar is a limit point of xk. Okay, but now by the definition of Armijo's rule, okay, this says, if we look at go back to Armijo's rule from the previous page, so this is at the stopping point, this would be k, this would be alpha k, this whole thing is xk plus 1, and so this is alpha k. So if I look at f of xk and take this thing to the other side, take this thing to the other side, f of xk minus f of xk plus 1 will be larger than sigma alpha k times the gradient squared. Okay, so let's plug that in. F of xk minus f of xk plus 1, if I use Amigo's rule, is guaranteed to be bigger than or equal to alpha k but the left-hand side is going to 0. And the right-hand side is smaller than the left-hand side. So the right-hand side also must go to 0, right? So using star, this equation right there, we get that sigma, sigma is just a number between 0 and 1. So just focus on the sequence alpha k times the gradient squared. This must go to 0 as k goes to infinity. So what does that give us? Okay, so now let's suppose the index of the subsequence that's converging to this x bar, the one that we candidate, the limit point that we pick. Let's call that script k. Okay, so by the continuity of the gradient, now we'll use the continuity of the gradient, not of the function, but the continuity of the gradient. And by the assumption that the gradient at x bar is non-zero, we have that if I look at the limit along this subsequence, right, at which xk is going to x bar, and I look at the gradient squared along that same sequence. Now, by continuity, this has to go to the limit of that sequence, the gradient at the limit of the sequence. And by our assumption above, we assume that this is non-zero. So if I look at the sequence of gradient squared right, along the subsequence rather of the gradient squared along the index at k, this is going to something that's not equal to 0. Okay, so now let's go back and look at this. I have that the product of these two things is going to 0, but this guy cannot go to 0 along the subsequence that takes me to x bar. So along that subsequence that takes me to x bar, alpha k must go to 0 because the product is going to 0. That's the only way that can happen. So if I look at the limit of alpha k, as k goes to infinity along the subsequence script k, this must equal 0. Okay, now this is important, and we're going to exploit this. So we're going to exploit this fact. Sorry, I tried to draw a box, but I couldn't quite do that. So we're going to exploit this fact to get our contradiction. Okay, let's see how we do that. We have to exploit this fact and of course also the condition that we are using Armyho's rule. So we'll do that. Okay. So remember that alpha k is alpha 0 times beta to the mk. So I've started with alpha 0 at time k, and I've reduced it successively mk times until I got to alpha k, which is beta to the mk times alpha 0. So if I take the log of alpha k, I get log of alpha 0 plus mk times log of beta. Okay. So if I look at mk itself, I can write mk as log of alpha k minus log of alpha 0 divided by log of beta. And this we saw is going to 0 to, since the alpha k is going to 0 along the subsequence, log of alpha k has to go to infinity. Okay, so basically mk is going off to infinity, right? So if mk is going off to infinity, then and why is actually you have to be a little bit careful here. If I look at maybe I should explain that. Log of alpha k, if alpha k goes to 0, is going to negative infinity, but I'm dividing by log of beta. Beta is between 0 and 1, so I have a negative quantity here. So the ratio will go to plus infinity. Okay. All right. So if mk is going off to plus infinity as k goes to infinity, then eventually it has to be bigger than 1. Agree? So there exists some k bar such that mk is bigger than 1 for all k bigger than k bar and k belonging to the subsequence strip. So, okay. Agreed? So basically, all this is saying is that eventually I'm going to at least take one step size reduction in Armyho's rule for all k along this subsequence eventually. So if I look at k bigger than this k bar, Armyho's rule at least reduce the step size once. So what this means is that if at time k I didn't reduce the step size, or if I backtrack by 1 or forward track by 1, I should say, by dividing by beta instead of multiplying by beta, then I should not meet the Armyho's condition for stopping. So that's what I'm going to do here. So here I'm going to say I start with xk, and instead of subtracting out alpha k times the gradient, I'd subtract out alpha k divided by beta. So I'm going to just the previous step size that I chose at time k, which didn't quite meet my conditions, which is why I had to take one step size at least, right? So I'm guaranteed that this is going to happen. because I would have taken at least one step size at time k if k is bigger than k bar. So, since the condition for stopping hasn't been met, instead of having this guy be bigger than or equal to, I'll get less than sigma times the alpha k, because I have, this is not alpha k itself. At alpha k, the inequality has gone the other way, but one step before it would be less than. Everyone see this logic here? And this holds for all k belonging to script k and k bigger than k bar. Okay, so this is basically the most important step. So if you didn't get it, ask a question and ask me to repeat. Okay, looks like everyone got this. Okay, good. So I'm going to exploit this now to get a contradiction. So by Taylor's theorem, if I look at this is x minus something. So I'm looking at this quantity here, right? Sorry, looking at this quantity here. I'll expand that out using Taylor's theorem and see what happens. Okay, so I'll get that as f of xk minus the gradient of f. Now, rather than taking the gradient of f at xk, if I want an exact expression, Taylor's theorem, first order exact exact expansion, I'll have to, rather than xk, I'm going to take some point between, so this should have been xk, sorry. Yeah. That I take some point between xk and this xk minus alpha divided by beta gradient of f of xk. So another way to think about that is, I'll write this as alpha bar k divided by beta gradient of f of xk. So I'm taking the gradient of f at this point, and then I have to multiply it by the direction, which is alpha k divided by beta and gradient of f of xk. So this is Taylor's theorem. So this alpha k bar, this is for some alpha k bar belonging to the interval 0 alpha k. Okay, so if I didn't have this thing here, I just had gradient xk, then I would have to add the little o of the norm of the squared, right? But if I now choose some value between 0 and alpha k and put that in there and subtract that out, then I end up getting an exact expression by Taylor's theorem. Everyone see that? So now going the other way, so if we look at what I've done is upper bounded this quantity. So I'll take this quantity and to the other side and subtract out xk from it. So if I did that, then I get that this quantity here is now going to be upper bounded by, okay, actually another way to look at it is, if I take this thing here, this quantity here, move it to the left-hand side, and then I get that this is equal to f of xk minus this. So that's exactly what I have here. So this gradient quantity here, this must be less than this. Okay, so I'm going to plug that in. But then I'll cancel off the alpha k divided by beta here. So if I did that, I get this is less than sigma times gradient of f of xk squared. This holds for all k belonging to script k and k bigger than k bar. I'm almost done now. Trying to get a contradiction. So let's see what kind of contradiction we end up with this statement. So now let's take the limit as k goes to infinity on script k. So if I take the limit as k goes to infinity, then what happens to this guy? Sorry, on script k, what happens to this guy? Well, alpha k bar, which is less than alpha k itself is going to 0, so alpha k bar has to go to 0 because it's between 0 and alpha k. So alpha k bar is going to 0. If alpha k bar is going to 0, then this thing goes away. So you're left with just the gradient of f of xk squared on the left-hand side. On the right-hand side, you have sigma times the same quantity. So if you take the limit as alpha k, as k goes to infinity on script k, you get that in the limit, what's happening to xk is that it's going to xk bar. On the right-hand side, also xk is going to xk bar, right? And by continuity, grad f of xk is going to grad of x bar, f of x bar, on both the right-hand side and the left-hand side. So you get that grad of f of x bar squared is less than sigma times grad of x bar squared. Again, because xk is going in the limit to x bar, and alpha k bar is going to 0. And this sigma is strictly less than 1. So this is again strictly less than, strict is important here. So what we have basically shown is that this quantity is strictly less than itself, and it's non-zero, right? That's what we made the assumption, it was non-zero. So we get a contradiction. So the only way this can happen is if you know, the grad of f of x bar is 0. Okay, so that means basically x bar is a stationary point. So if we assume that it's not a stationary point, you get a contradiction, so it must be a stationary point. Questions? If you didn't quite understand all the steps, okay, just go through the proof again. Okay, it's a little long, one of the longer proofs that you'll see in this course. And then in the homework, I ask you to do a small variant on this proof, which is actually very, very straightforward. Okay, once you understand the steps of this proof, you know, it's going to be very easy to do. So I'll put that in the homework. So that will also give you another chance to look at this proof again. Any questions?
Excuse me?
Yeah.
Yeah. Can you explain again the light therefore we get?
About the last step? What?
The last step, yeah.
Yeah, the last step again. Yeah.
Next page, yeah. Yes, the light from therefore we get. I understand that we're moving from the term from the right to the left.
Yeah.
Raise the alpha k and beta in this case.
Yeah. So basically this, okay, just move it to the left, and so and this is basically what you have up here, f of xk minus this. So this is the same. This quantity here is the same as that. So we conclude from this inequality that this is less than this. But of course, there's this alpha k over beta, which will be on both sides. So maybe I'll write that down here. Alpha
Oh,
k.
I see. Yeah.
And they cancel.
Thank you.
Right. Okay, so let's say a few things about this. Okay. Okay, first of all, any step size selection rule that decreases f by more than Amicho's rule inherits the convergence properties. And you'll actually, in your homework, you'll look at the optimal selection rule, the optimal line search. So once we prove that Amicho's rule converges, right? Xk converges to a stationary point. It will also hold for any other rule for which you get, for which the step size, for which the function reduction is larger. And of course, optimal line search is the best. Okay, and I'd like you to actually do that in the homework. It's actually just a couple of lines, and you can conclude that. But that's true, basically. So once you've shown convergence of the Armingholt rule, anything that does better than Armingholt's rule is also going to converge. Okay, so that's what you're going to show in the homework. Also, you can replace this negative gradient. So instead of using steepest descent, you can use decay. Anything that has a positive projection along the negative gradient. So any what's called gradient-based method will also inherit the convergence properties. So you can see the book for that. Okay, so the book actually does the more general proof. It's a little more involved, and it doesn't really convey anything new. So that's why I didn't do the proof for the general case. Now, the result does not, I should have said result here, not lemma, but anyway, I guess I'd called it a lemma before. But the result that we just showed does not imply that xk has finite limit points. It just says that if xk has a limit point x bar, then that x bar must have gradient 0. But it doesn't say that the xk has a finite limit point. And so this can happen even though f of xk might converge, but that doesn't mean that sequence xk itself converges. And here's actually a very simple example of that, right? Take a function that looks like this. Okay, so as this is a function that's lower bounded by 0 and is actually converging to 0 as x goes to infinity or x goes to minus infinity. So basically this is 0, the origin. So as x goes to plus infinity or minus infinity, but the function goes to 0, but it only attains that in the limit. Right? Think of something like e to the minus x, e to the minus mod x, right? Or actually, that's not a very good example. E to the minus x squared is a better example, right? So it's continuously differentiable. So it goes to 0. So basically, even though in the limit f of xk is actually approaching 0, xk itself is blowing up. So the sequence need not have a finite limit point. But if it does, you're guaranteed that the gradient is 0 there. Now, even if xk is bounded, it could have multiple limit points, and we discussed that earlier. And so convergence to a single limit point is not guaranteed, but it can be shown that if you have, and of course, if it's a convex function, it doesn't matter which limit point you go to. They're all guaranteed to be a global minima. So it does, and even if you shuffle between them, it's okay, right? But it can be shown that if your local minima that are isolated stationary points, if they're isolated, in other words, it's not like a flat region in my X space, they are the ones that tend to attract most gradient methods. So once you get close to one of these points, you actually will end up at that point. And that's called the capture theorem. And it's basically a technical result that you can check out in the book. So that just tells you that in practice, it's not too bad that you're going to these kinds of stationary points. Of course, if f is convex, every stationary point is a global minimum. So if xk does not converge, we can still get arbitrarily close to the global minimum. We may be shuttling between two stationary points, but that's okay. Okay, at the time you stop, the function value is not going to change very much. That's going to be a typical stopping criterion for gradient descent. And at that time, even if the xk shuttled between two stationary points, both those stationary points are global minima. So it doesn't matter which one you get. Okay. Any questions? We're almost out of time, but can still take a question or two. Okay. So again, you know, the textbook is huge. Okay, it covers a lot of material. My goal will be to actually give you some key results. Okay, and they may not necessarily be directly results that you'll see in the book, but based on the results that we study in class, you should be able to go and read the more general results or more details or different variants and so on. So I would encourage you to do that at some point, you know, and you might see a few variants in your homework as well. Okay. Questions? All right. I guess I'll see you guys on Thursday.